All right po. So good morning din po. I'm Jokey and I will be discussing to you about the process that we have developed when it comes to uh, adopting hybrid manufacturing with the aid of additive manufacturing sa ating current metal casting processes. So uh, first let me and then later we will be discussing the considerations on the design and modeling and also the 3D printing of the part. So let me proceed with the presentation. First, let me define metal casting. It is a process where metal objects are created by pouring molten material into a mold and allowing it to solidify. So some of the common processes used in metal casting are sand casting, investment casting, die casting, and centrifugal casting. So each of them have different mechanisms and each of them have different advantages. So pattern making, of course, if you want to cast something, you need a representation of the part that you want to make, and that is called a pattern. So patterns are used in the creation of molds, particularly in sand casting and investment casting. Patterns can be made from various materials such as ferrous metals, aluminum, plastic, wood, and even wax. So that's the one for investment casting. So traditionally, how we did patterns was we make it out of wood by carving wood or maybe cutting up different shapes and putting them together to make the shape, the final shape that we want to make. So this was how it was made back then, or until now. Actually, it's still being used. Now, the concept of additive manufacturing. Additive manufacturing is a process that deposits material layer by layer to build the desired part. So it's commonly known as 3D printing. It has a wide array of materials, including common plastics like polylactic acid, ABS, the plastic that you use for Lego, that's ABS, PET, and engineering plastics like PEEK. PEEK is being used as a substitute for aluminum because it can be equivalent to aluminum's strength without the weight. Okay. Carbon fiber reinforced nylon, which is also very good for engineering purposes because it has carbon fiber reinforcements. It's also used for printing resins and ceramics. And now, with modern technologies, we can also already 3D print even metals. Metals like stainless steel, aluminum, tool steel. A lot of metals are now being developed for use in 3D printing for special purposes, and a lot of other things. Even food, concrete, clay is being 3D printed now. So, what are the uses of 3D printing? 3D printing is most ideal for rapid prototyping. I will be discussing on that later. It's also very good for uh, printing common plastic materials, the ones that are inexpensive, because of course one of the main things that if you want to make a prototype, especially if you're from a small business or even if you're a student, is the cost of making your product, your prototype. But with 3D printing, it allows you, because it's commonplace now, it allows you to make your parts in very inexpensive means, because you're able to just buy cheap plastic material, and as long as you have access to a 3D printer, which also comes cheap nowadays, yung plastic 3D printers, you can be able to make your prototype. And the additive nature of the process leads to less material usage. So we can compare it to machining. If you want to make something out of machining, you remove material from 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 a starting block. So that's the part that you remove, the chips is waste. You can recycle it, but it's of less value. Okay? So if you do additive manufacturing, you only use material for the shape or for the form of the part that you're going to make. So that's one of the advantages. And also it's able to do intricate geometries. This is one of the, I think, one of the most value adding things that additive manufacture can offer, because if you're familiar with machining techniques or casting techniques, you always have to consider the geometry of the part you're making. If you're doing casting, you always have to consider if the pattern of that part can be withdrawn out of the mold. So you have to think of the geometry. Same goes for machining, where you have to make sure that your cutting tool will have access to the features that you want to machine. So for example, if you have an internal surface that goes very deep and it might go through a uh, very tricky path going inside, it may be impossible or it may be very difficult. It might be possible, but it might be very, very expensive. For 3D printing, it removes that limitation, because 3D printing, since it builds the part layer by layer, there's virtually no limitation on the shape or on the geometry of the part that you want to make. So it's also a useful tool in creating patterns for mold. So that's why we have this seminar right now, because one of the things that we found use for additive manufacturing is for it to be used as an alternative to traditional means of making patterns. And I will be discussing that in the next slides. So traditional and 3D printing pattern making. So that when it comes to design, the technical aspect of designing the patterns, they are similar actually. Because if you make a casting design, you still have to make sure that the flow of your material going into the part is controlled to reduce the turbulence. You also still have to make sure that the feeding of the metal from the risers is also effective. When it comes to that aspect, there's no difference while designing or in designing the 3D printed pattern and the wooden pattern or even the CNC machine pattern. Because when it comes to the mold, it's still going to have the same shape. The difference is how you're going to make it, or the manufacturability of the patterns that you are going to make. And with that manufacturability comes the factor of costs and the factor of time that you might be able to save when you choose one over the other. Okay, so for traditional pattern making, it relies heavily on the skill and experience of a pattern maker, especially for wooden patterns, to properly translate the part drawing to mold to the pattern maker. And that pattern maker interprets the 2D drawing. So, for example, you have a flange or a sleeve. He takes the diameter of one part and then draws it in a one is to one scale in his in the wood and cuts it out. But along that process, and once he assembles all those shapes to make that full part that you're going to make, it might be dimensionally accurate for each time that he drew each shape. But when he put it together, he might not have been able to consider like the concentricity of the flanges or the wall thicknesses of the parts. And that may lead to some problems when it comes to other subsequent processes like machining. So when you do it with 3D printing, a computer makes the model. A computer makes the part. And that part that it's making comes from an instruction that came directly from the 3D model that you drew in the computer. So there's not going to be any deviation when it comes to the shape and the dimensions of the part. Because it's made exactly to the intent of your design. So in recent years, of course, with the advent of CNC or computer numerical control, it has already been possible to translate a 3D model to make it into a pattern directly. But that was made possible by CNC machining. So still the same, you have a 3D model and then you translate it into a program that can be understood by the machine. That's called the CNC program or the toolpath program. So the one with the G codes. Okay? And then using that, you start from a block and then you get cutting tools, different kinds of cutting tools like drills, end mills, face mills, to be able to sculpt that shape that you want to make. So if you want to make something like a pulley or a wheel hub, You start from a block, maybe a block, a cylindrical block or a square, a cube, and then you start you start cutting out the unneeded material. It's effective because you get a very dimensionally accurate pattern. The only problem is it's very, very expensive and it takes a very long time depending on what size of starting block of block you started with. There also has been other methods that works around this. They cast the part to make it near net shape. So if you have something like that shape, uh, that wheel shape, they just add like 2 millimeters on the surface for the machine to remove. But still, that also lengthens the time because you also have to cast that starting block to near net shape. So there's when it comes to the time that it takes, there's very little ways around it to really shorten the preparation of such patterns made from CNC. But the only thing that can justify that length is if you have parts that go by the volumes of tens of thousands, hundreds of thousands, because it might very well be worth that time and that cost that you spent on that pattern. But if it's like 100 pieces, or maybe 500, or maybe 50 pieces, and you need it to be very accurate, you can you can't justify the cost of making that. That's the one of the disadvantages of doing CNC 3D CNC pattern making. But one big advantage is that since you're able to machine like harder parts like steel or aluminum, stainless steel, it's much more durable also. So for 3D printing assisted pattern making, it's a rapid prototyping technology. So you have faster prototype turnaround time, and it's very very easy to iterate. For that same shape that I've shown earlier, what 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 CNC machining takes about 2 to 3 months, you might be able to make it in like 2 weeks tops for that same shape and size. So it's also able to do complex geometries more accurately. Uh, Again, there's less material waste compared to subtractive manufacturing since you're only using material that you need for the shape of the parts. Ergo, it also uh, leads to less tooling cost. For you to be preparing the same pattern from wood, from CNC machining, and from 3D printing, it has the least tooling cost. So now they've already actually used in globally they've already actually used additive manufacturing as one of their standard processes for pattern making. And we've also begun using it since we in MIRDC we also have our own foundry and we do R&D, and we've catered other partners in making some of the products like we've developed an electric kick scooter, and some of those structural parts were made from cast aluminum. The ones you see with labels there are made from cast aluminum. So let me show you the overview or how it works. So first, you begin with having the 3D models of your parts. That's where you begin, of course. Uh, if they give you something like a real sample from like a spare part, and they want to make that part again, you have an option to either draw it using CAD modeling software, or if you're not able to draw it because the shape is so complex, you can also do 3D scanning to be able to come up with 3D models, because the 3D models is the information that you're going to send to the software that is also going to give the instructions to the 3D printer where to add the material. Okay? So next, once you have the 3D models of the parts, of course you're going to make patterns. The 3D models of the parts is different from the 3D models of the patterns in that you need to add different features. Like if the final part of the 3D model that you have is a 3D model of the final part where you have drilled holes, the machined features like drilled holes, machined flanges, machined walls. You have to remove all those machining features to make it a casting 3D model. And then from the casting 3D model, you also have to include like the drafts for drawing in the mold making. You also have to include the shrinkage allowance because of course, as you know, anything that cools will also shrink. So you also have to factor in a scale that will make sure that when your final part or final casting cools, it will be to the uh, intended dimensions. Okay. So once you have the 3D models of the patterns, oh, there's also an optional uh, process between making the 3D models of the parts and 3D models of the patterns. And that's simulation. Okay? So traditionally, ang ginagawa is you have a casting, you have a casting design, and for you to be able to make sure that this casting design works, you have to do actual melting. You have to make the actual pattern, and then you have to make an actual mold. You have to do actual melting and uh, pour to make an actual casting for you to be able to measure and for you to be able to evaluate if your casting design works. Does the final product have no shrinkage or no defects, no bubble defects, voids? If it does not work, you go back to the board and then you change the design, you change the pattern again, you melt again. That's how it was done before the advent of simulation. Now you can do all of that virtually. So you feed the information, your process parameters to the simulation software, and then the simulation software will be the one to calculate all of those flow characteristics and all of those cooling characteristics, and will show you where the defects or if there are going to be defects in your casting. And if there's going to be a defect, it's just as easy as going back to your drawing without really making anything physical yet, like patterns. It's all done virtually. So you change it again, and then you try to do simulation. You do simulation again until you get your casting design to work perfectly. So once now it works perfectly, that's the time you make a pattern design out of the last design that you've made that worked. And then once you have made the pattern design, it's just as easy as sending those 3D models to your 3D printer to print it. So now you do 3D printing. And after 3D printing, you do post-processing. Post-processing means just cleaning up your 3D printing. Because if you can see that the freshly 3D printed parts, you're going to see lines. Because since it's made layer by layer, you're going to see the layer lines of the 3D printed part. And those layer lines are going to show in the final part if you don't remove it. At the same time, it's going to make stripping the pattern out of the mold much harder because it it causes friction. Okay? And more importantly, bare plastic, if you use something like a chemically bonded process like Furan or other chemical binders, the acids used as catalyst for those binding systems might eat up the the plastic, might react with the plastic and might melt it or might soften the plastic. And also, since you're going to use sand as a molding agent or sand as a molding material, sand is an abrasive medium. Okay, that's why they call it sanding because it's abrasive. So if it's abrasive, you also have a problem of wearing out because it's plastic. So what we do is we spray or we paint we coat the 3D printed patterns with hard epoxy primer. So it's able to remove all those three problems all at once. It makes the pattern chemically resistant. It makes the pattern abrasion resistant. At the same time, we can be able to sand it to a point where it's very smooth and pattern stripping from the mold is is done easily. Okay. So once the post processing is done, we send it to the molding area for molding. And then the usual casting process, we melt, we cast, we do machining for parts that need machining, and then we do QA inspection using scanning technology. And then you come up with the final part that's uh, that's already acceptable for use for its intended function. So this is the pattern modeling part. So the technical design considerations are the same as conventional. So yung gate, the gate and sprue sizing, if you have a calculation for that, uh, there are books that show you that the calculations for how to calculate the proper flow or the proper entry of the molten metal into your mold or into your cavity, such that it does not cause turbulence and does not cause air to go into your casting. There's also proper calculations for feeders or risers for you to be able to appropriately size your riser such that even if shrinkage happens in the casting, there's always a reservoir of or a riser that will compensate for that shrinkage. So here's an example of casting simulation. I'll show you an initial model, and the animation on the right shows you what is the sequence, what the sequence of solidification is. So what can you notice on the right, on the left figure? It says there that you have a shrinkage problem. The dark red highlighted areas. The simulation says that you have a shrinkage problem on the joint of the flange and the casting wall. The reason for that is because uh, if you can see the sequence of solidification, the wall has already solidified and this has not yet finished solidifying. Even if the riser is still feeding, that molten metal can no longer reach or feed this part because this has already solidified. So no molten metal can go past the material. So uh, the effect is since this is still cooling, it will still shrink without without compensation of the metal. So you have shrinkage problems here. So when we saw that, we decided to do something to address that shrinkage. So what we did is we changed the orientation of the casting and we changed the the location of the risers such that even if this solidifies, the riser is still the last one to solidify and it's still able to feed the thick part which is the flanges. So this ensures that when the casting completely solidifies, as you can see on the final shrinkage evaluation, the only one that has shrinkage is of course the riser because that's the goal of the riser. It's the one to shrink as a sacrificial part. So that's how you do. That's just a simple illustration on how simulation works. And then once we're satisfied with the results of the simulation, of course, it's not only shrinkage. There's also simulation for uh, gas inclusions and hot tears. A lot more things, cold shots. So you can choose what defect you want to see, and then once all of the defects are solved, then you proceed to your 3D printing or to the design of your patterns. For 3D printing, your what you will need to consider is how strong does your pattern need to be, and that decision depends on the volume of the part that you want to make. If it's just a simple jobbing part that might just require like 50 or 100 pieces, you you define or you set your parameters for 3D printing in such a way that it's it's appropriate or it's just enough for you to be able to make those 50 pieces. Okay? So you define it, you do that by defining the wall thickness of the prints and also the density or the infill density. If there's more, if it's of a bigger volume, then do the 100% density to make it really rigid and solid. But if it's just like 5 pieces or 10 pieces, you can get away with like just 50 or 40% density. You also need to consider the orientation. In 3D printing, there's something called printing supports. So since you're depositing layer by layer, if you have features like overhangs, you need to have support material because you can't print on air, right? So for you to be able to deposit the the plastic, there's something that needs to hold it, that overhanging part. So you will have support. So since one of the goals is to lessen or to reduce the cost of making the pattern, you have to find uh, the best configuration of the material such that there's minimal supports because supports are going to be waste. There's minimal supports. At the same time, you will also need to consider uh, the strength of the part that you're printing because 3D printing is not an isotropic process, meaning the strength of your part on this like x-axis, y-axis, and the z-axis are different because the z-axis is where the layer lines meet. So it's the weakest parts of the pattern. So if you imagine for you to be able to strip a pattern out of a mold, you're going to need a vertical force pulling the pattern from the mold, and there's friction and all of those things that is keeping the pattern from being withdrawn from the mold. So if the layer direction is parallel or perpendicular to that direction, that's where it is weakest. So you might also need to consider the printing direction in such a way that you are also considering how is it going to be used, or what are the forces that it is going to be uh, experiencing when it comes to its function. Another limitation also for 3D printing is of course build volume. So uh, some 3D printers like desktop 3D printers have very small volumes, like maybe less than half a meter. Say for example, you only have a 3D printer that can build a maximum of 300 mm by 300 mm by 300 mm. And you have a part like maybe half a meter long and wide and high. So how do you make that part considering you only have a small part? So what we usually do is we segment the part that we're going to make and we assemble it later. So something like the one on the right side. Uh, of course, the issue about this is as 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 you segment it into more parts, there's going to be error in the mating because of course it's not as accurate as building the whole part as one whole part. So if you make it as an assembly of smaller parts, you introduce errors in the dimensions. So you also have to be careful about that. And once you assemble your part, make sure to also still measure the part that you make and make sure that still uh, is correct. Co- Considerations on 3D printing, things like hole sizes. There's a maximum hole where the circularity suffers. Beyond it, the circularity suffers, and also for overhangs and angled surfaces. So this one is for post processing. By the way, we use 3D printing for two different types
Babae si
or
Diyos.
for two different technologies of
Lalaki.
casting. First one,
Sa
we
clinic.
made patterns for sand casting. Okay, so for sand casting, as you can see there, we put epoxy coating on it for it to be able to be abrasion and chemical resistant. For the other one is lost PLA. So imagine it like lost wax investment casting, but instead of wax, we 3D printed the plastic patterns. And at a certain temperature,
Sabi ni
that plastic pattern
Isabela,
burns
babae
without
nagkakala.
residue. So essentially, it's
Kasi
just like 3D
pinagdala,
printed.
pinagbuhay, kakaya.
It's just like lost
Ang ina
wax,
kasi.
but
Nakawin
instead
din.
of wax, it's
Sahod
plastic.
din. Ate.
So it still underwent the same coating, ceramic coating technique and firing
Nakamula
techniques,
sa simbahan.
and we're able to come up with something like this,
Simbahan sa
an
ibang
impeller.
klase.
Because we can also
Payat
make
lang talaga pero husay ano.
an
Mahusay talaga
a
eh.
sand
Siyempre ako
casting
pinakamahusay na
pattern for
naglaro.
the impeller, but it given the very short time that they gave us,
Inikot mo, yan
we
ha.
opted to just do 3D printing for 10 pieces of impeller patterns.
Sino mo dito? Wala napagod si Ike.
So this one's 3D part. This is the set of parts that our partner wanted us to make.
Kasi
They needed
nakalaban
10
natin na pagka
sets of this one.
engineering, nakalaban natin.
The problem is
Lagi
some
sa
of the
akin.
parts
Isabel,
were made from
ito naman.
aluminum, and unfortunately the
Ikaw
aluminum
talaga
they
yung
used
maglaro
was
ko.
not a grade appropriate to be used at sea.
Mahina na nga
This
siya,
is a
may sabi na
propeller water jet propulsion
ano
system.
nga eh,
Okay,
patay na.
it's used in vessels to be able to do
Tingnan nila lang.
propulsion. So only one of the or only two of the components are made of stainless steel, which uh, did not fail. But all of the aluminum parts they failed. So as you can see, there's a broken piece of the casting there. So they asked us to make a few more sets, but they did not have drawings. So what we did was we used a combination of CAD modeling, and also for this kind of geometry, which you can really do measurement and CAD modeling there because the geometry is very complex. We did 3D scanning. So that's an example of a 3D scanner. So there's a camera, there's a probe that has light, and it projects light onto the subject that you're measuring, and depending on how depending on the way the light bounces on your model or on your sample, it returns information to the software to be able to generate a 3D representation of that model or of that sample that you're scanning.
Pabisalang ka lang ha.
So that way we were able to get accurate 3D models for the parts we want to recreate. For 3D pattern modeling, as you can see, this is the final part. The one on the right most is the finished part model.
Betsa
So it
ng
includes
knowledge.
all the red surfaces are the surfaces to be machined. So those are drilled holes and milled surfaces. So for you to be able to do casting, you need to put machining allowance or machining stock. So you remove the drilled holes, and then you also add a layer or like 2 mm or 3 mm additional surface for machining. So that's the one on the middle. And then if you superimpose those two models, as you can see, you have already those machining allowances considered in the casting model, and also the holes. Same goes for this one. We removed all the machining features like the holes, and also we added, if you can see a line on the middle one, that's the pattern shaft. And then basing from the casting model that was just generated, we attach or we draw around it the in gates, the runners, the sprue, the risers. And then we come up with the 3D pattern assembly model. And of course, you're going to think of how you're going to do 3D printing of this casting design. So you're going to segment it in such a way that you can 3D print uh, the all the components with minimal supports. At the same time, you can give the easiest way on how to strip the pattern out of the mold. So this is a simple geometry because it's just like a flange, two flanges. When the design gets more complex, you also uh, have to be more creative in making the pattern. So for this one, as you can see, there's a lot of elements on how to make the internal cavities. So you have a series of core boxes for you to be able to make the complex features inside the casting. And you can see it on the display at the back. So each of this is what we did. Like since we don't have a printer as big as this one, and we only need the pattern cavity to be accurate, because that's the only thing that the only the casting needs to be accurate. These are just like baseboards for the sand to land on. So we only 3D printed these parts with the accurate 3D printer, and uh, this one I think we just used wood. So no need to do 3D printing parts that for those parts that don't need to be really accurate. So this one is the core box to make the scroll shape inside the cavity. And this is another one of the core boxes. And of course, if you consider how will you remove the sand core after molding it, you have to be able to subdivide the core box in such a way that you can easily, or not easily, but you can take out the sand mold. So that's how it ended up being the core box. Like it's like an Iron Man assembly. Then we do simulation. As you can see there, you can you can color code, or there are different scales for temperature, the solidification sequence, the shrinkage, some for slag, some for void, some for hot tears. So this one is for the impeller. As you can see here, there is another advantage for this is quite not conventional, but there's another advantage for simulation. As you can see here, there's shrinkage. So there's a defect in our casting. But we did not change the design anymore, because considering, and we know for a fact that the final part, there will there will be no material around that part because we're going to do boring on that part. So there will really be no casting once you machined it off. So even if there's shrinkage there, it's no problem. So it also allows you to do those decisions, like there's a shrinkage there, but this part is going to be non-existent in the final product. Or this part is not going to be a functional area of the casting that you're going to make. So it allows you to make those decisions. So you're not going to spend too much on making the risers bigger, because bigger risers also leads to less yield. You're melting much more metal just to put onto the risers. So you can be much more optimal with your designs, especially when it comes to melting. So this is what we mean. There's not going to be any material here, so even if there's shrinkage, it's not going to matter. The 3D printers we made use of One is a desktop printer. It's called an Ultimaker S5. So the build size is 330 by 240 by 300 mm. It's meant to make smaller, more. Hello. Okay. Uh, and these printers are really used for industrial settings for prototyping. It makes use of fused filament fabrication technology. So if fused filament fabrication, it's the concept is just like a glue gun, but instead of glue gun, you have a spool of filament, and instead of a hand pressing the trigger to make the melted glue come out, it's a computer with the instructions of the 3D model that you're going to make. So the materials range from common plastics like PLA and ABS to high performance engineering plastics like PEEK, Ultem or polyether imide, uh, and even composites. Like you can make nylon material, but you can reinforce it with continuous or chopped carbon fiber. So you can just imagine having something like a very thin part, but it's as stiff as aluminum, and it can substitute aluminum. Uh, and also even metal infused plastics. The material we used for the patterns were PLA. It did not. PLA has very weak chemical properties, but it did not matter because we. That's why we coated it with epoxy primer. And for larger prints, we used our Cosine AM1. It's 950 by 750 by 480. The advantage with this, it makes use of pellets instead of filaments, which are much cheaper because they're the same pellets that you use for plastic injection molding. So the extruder, instead of melting and extruding filaments, it melts and extrudes pellets, and that's how it does the 3D printing. So the materials also range from PLA and ABS peak, the same ones as uh, Ultimaker, but it also has more options because because you have the option to do to make or to melt or to extrude industrially available uh, plastic pellets. Okay, so polycarbonate, ASA, ABS. So this is how it went, the 3D printing of patterns. For the impeller, uh, blade profile is non-planar and thin, so it's very tricky to make a sand casting pattern out of it. There's also a lot of overhangs. If you do it with sand casting, you're going to have difficulty in drawing the pattern out of the sand mold. You're going to make like the molding is very tricky. It's not just a straightforward molding process if you're doing geometries like this. So what we did is we instead opted to do uh, investment casting on this one with the lost plastic process. So for sand casting, this is how the pattern may look like if we did it with that with sand casting. So that's why we opted for investment casting. So we made 10 sets of plastic patterns, and then we did ceramic coating on them, burned off the plastic, and then poured molten stainless steel onto the ceramic molds. This one also has very complex geometries. If you can see the one with the color coding of red, yellow, and green, that's the draft analysis of the part. So as you can see, there's no way you can draw the pattern simply from the top or from the bottom. So the pattern turned out like this. You have to draw it like into several different parts because one goes out easily this way, one part goes out easily this way, the other part goes out easily this way. So there's a sequence of drawing the pattern from the mold. Of course, there's also, since the shape is complex, there's also an option to do investment casting on this. But unfortunately, the printing time to make the investment casting pattern is very long, and we need to make 10 of those. It's very wasteful also because we're going to burn it off anyway. So we opted uh to do sand casting instead. So this is the parameters you consider for 3D printing. The wall thickness and the density of the pattern to be able to dictate the strength of the patterns that you're going to make. So these are observations that we've made for those made with very thin walls and very low densities. Of As expected, they tend to to break much easier. And for those parts that we did with higher densities and larger wall thicknesses, there's very little wear observed.
Sir Boring, si JC po. Ano dyan?
This is the post-processing part. And then after we've prepared our patterns, we sent it to the molding line for molding, and then melting, casting. And finally, for those parts that need machining, we sent them to the machine shop for machining, and then did final QA inspection using the same scanner that we used for making the models. Because we already have a 3D model for the ideal shape of the casting. When we scan the actual castings made from that model, you can superimpose those two models to be able to check whether there are deviations from the intended dimensions. So that's what you see on the lower right side. It color codes the areas where your surfaces went over or under. Meaning if your part thickness, or if the surface went over the ideal surface, it codes it, it colors it red. And if it went under, it colors it blue. So if example you have a machining allowance there and it's colored blue, your machining allowance might not have been enough. So you have to make corrections on your pattern to make up for that shrinkage. And this is the final assembly of the parts that were made from 3D printed 3D printing assisted hybrid manufacturing. So just to compare, actually they're the same. The workflows for each. Actually, you can also do 3D. I mean casting simulation for the traditional process, even if you're using wood. But if it's really much easier uh, to get a hold on things if you make the development process just on a digital environment virtually, because if you make like if you use the conventional process where you don't do simulation and you make the actual parts, there's going to be lots of noise in your data, especially when you evaluate the parts. At least for this one, there's like a constant set of calculations that will prove that the results of the simulation is balanced. So there, there's really a big advantage when it comes to the hybrid workflow. So for casting, simulation reduces iterations in the casting. So you're able to ensure that the casting design is viable and as close to the final intended part as possible. And what 3D printing offers is that it serves as a viable alternative to pattern making for low to medium volume production. Of course, if you're going to have like large volumes, we're always going to tell you that you go with machined CNC patterns because it's well worth it to spend for that if the volume is that large. But for low to medium volume parts, like for jobbing parts, you can get away with 3D printing, with the dimensional accuracy that's very good. So there, we've gone like from 3D models up to the final actual parts, which you can see there at the back. So that's all for the process. Thank you very much for listening. I think if you have questions, we can also entertain.
Thank you, Sir Jokey. Actually, there's a question here from, hindi ko na mention kung sino. So, ang question niya is, what is the cost comparison of 3D printed pattern to an ordinary wood pattern?
Unfortunately, we don't have data yet because for that uh, to be compared, we also have to like ask around for wooden patterns. But I think Sir Lems has some idea.
Okay. So actually, the cost of we are looking here at the cost of overall new casting development, not just comparing the wooden pattern and the 3D printed pattern. The idea here is that during product development, you have targets for cost, you have targets for uh, manufacturing lead time, you have targets for development speed, because as if you can develop it as fast as possible, you can say capture the order, or you can limit your cost. I think that's called opportunity cost. Okay, so with 3D printing and simulation, um, the iteration you needed to perfect your design is going to be 100 in the virtual world. So imagine if you're going to make a sand wooden pattern, yung the skills of the quality of your wooden pattern is highly dependent on the skills of your 3D of your pattern maker. The thing is, nowadays there are no more schools offering woodworking. So the quality of your wooden pattern is highly suspect. So the best thing you can do now is really to transition to 3D printed patterns, because the skill sets that are available now are mostly related to computers, computer modeling, computer operation. So you can easily find people who are the basic skills are already there. So you just have to train them on the considerations for 3D printing. So that's the really the reason why 3D printing is now more viable than wooden pattern making.
Okay, thank you, Sir Lem. Sir, another question. Does infill percentage affect the output of the casting?
Can you repeat that again?
Does infill percentage affect the output of the casting?
Yeah, as I discussed earlier, you just have to select the appropriate infill percentage, because the only thing infill percentage affects is the strength of the casting. So if, for example, you're going to use it for the first 10 pieces, I think it's going to do good because you have designed it to withstand. So it depends on the volume of what you want to make. If you want to make a pattern for a part that has a larger volume, you design the density or the infill density to be able to withstand that kind of volume. So the infill density will not affect like the geometry or Because what's only going to matter is the outside surfaces of the pattern that you're going to make that will give the shape to the sand that it's molding. So I hope that answers the question.
Okay, thank you, Sir Joki. Sir, another question from Sir Joseph and Cabo. Paano po ang choice of materials impact the additive manufacturing process and the final product?
If you mean the choice of materials that you use for 3D printing, again, I'll go back again to that volume of the part and the size. Idadagdag ko na rin yung size of the part that you want to make. Because PLA is relatively a weaker kind of, it's not really an engineering plastic. The only thing is PLA is very easily printed. So, yun yung advantage ng PLA. But if you want to really make something very, very durable, yes, it's going to matter. If you're going to use printer or plastics that are more specialized or more with higher mechanical strength, then it's definitely going to give you a longer life. So it's going to matter. The only thing is, if you use plastics with more highly specialized plastics, the printing parameters are also going to get more. I mean, the printing is going to get trickier. Medyo mas mahirap silang i-print na compared to PLA. So you also have to play around with the printing parameters for you to get the best printed patterns. So that's the trade-off for using higher grade plastics.
Okay. Sir, another question from our online participant. So, what software do you use for casting simulation?
Meron bang mayo?
Okay, so
Marami talaga, dahil wala naman
looking for
tatakbuhan
a
yun.
brand here. But there are a lot of brands available in the market. So before we used the top of the line, then it we had that license for several years. Then now we were able to buy the say not so expensive brand. So and for our use, it's more than enough. So yeah, really. There are a lot of brands. So Magmasoft, Novacast, uh, Procast. You can have a lot of choices. The only thing that will in your choice is maybe the cost, the support.
Nandiyan na siya
Yeah, but my our our observations here is that um,
Parehas naman ng
well,
salary.
it's really nice to have the top of the line. Sino bang ayaw ng Mercedes-Benz, di ba? But for our purpose, we found out that our brand, the one we are using, is its capabilities is way beyond our use. So we have
Ito
a
pag
lot
nakapagyan
more
bigyan
to
bayad.
use of its capability. So siguro kung hanggang dito yung capability niya, wala pa dito yung ginagamit namin. So yeah, you can visit us and see what our brand software we are using.
Kaya pala maganda rin yung restaurant.
Okay. Sir, another question from Sir Ronald Esmenda. What are the limitations of 3D
Ayan,
printing?
ano pala ano ba?
Well,
Kami nasa utak ko.
for now, the
Ay,
technology of
salamat.
3D printing
Kaso,
is
nalilito na.
already
Dalawa
way
lang
advanced
ayos.
as it started, say, 10 years
Kaya
ago.
ako na
So now, there are with regards to printing for pattern applications, the current technology of 3D printing now is very much capable of doing whatever we want with pattern making. So there's the only limitation is of course your knowledge and training and the limitation of the material, the processes, etc. But there are technologies suitable for whatever you want to do.
Ayun
Okay.
na. So just to add, what we've shown you kanina is 3D printing assisted hybrid manufacturing of making patterns. We 3D printed the patterns. I just also want to point out that there are also now technologies that can print the actual sand mold. So you skip the pattern making process. There are technologies that there's a bed of sand and a layer of a binder spray draws the shape of the part that you want to make on that bed of sand, and it already makes the the sand mold for you. So bubuhusan mo na lang siya ng molten metal. So it goes as far as that. Medyo mas may kamahalan lang yung ganung klaseng printer. That's one with like that might need bigger capital, pero yun nga, who knows, we might have one in the future, or maybe we can build one in the future. So if you find that you can have use for that, please do let us know your interest in having that technology also, because yun nga, it's one more way of having an agile manufacturing or prototyping process that we can have in our arsenal. So, yun po.
Okay, so there are lots of questions here, Pastor. So I think we can pick two or more questions from our face-to-face participant before we proceed po dito sa ating mga questions na sa mga online. Okay, sir, go ahead.
Sir, with regards po dun sa may investment casting, kasi po nasabi niyo na yun yung 3D printed po natin is pwede po siya sa investment casting. Di po ba nakaka-affect, sir, yung mismong 3D printed po natin na filaments dun sa mismong outcome po nung casting po, sir? Or lahat po ba, sir, nung filament na pwede kanina is wala pong magiging effect dun sa may magiging output na product, sir?
What we've tried really is just PLA, because we've already seen some other people online doing it. PLA, they actually have a name for it already. It's lost PLA casting. So that's what we've tried. We're also planning to try out other materials if it burns off with the same quality, meaning if it burns off without residue, just as PLA does. Because if it works like that, we have the option of making like bigger parts. Because PLA has a limitation in the size that it can make, because it might not be able to really just hold its own shape owing to the limitations on its mechanical strength. So we're also be trying to consider other materials such as ABS, ASA, PET, and use our bigger printers at the same time for us to be able to expand our capability, not just to PLA plastic. But when it comes to the quality, for PLA, there's no problem. We've tried it really to... We've actually tried to put it on a furnace and just to look at the inside of the cavity if there's really any residue of PLA left. There's really none. So that's what made us confident that we can proceed with the pouring of the impeller parts.
Sir, thank you po.
Burning it out, you can do it two ways. The first thing we tried is we put it inside a muffle furnace at about 500 degrees. And then we just checked if it burns out, and it burned out. But for the conventional way of doing like investment casting, there's a process that you fire you fire the shells before pouring to preheat also the ceramic molds. So there's no need for initial burn off. We just do shell firing directly, and then right there and then the PLA burns off. No expansion. Yeah.
We have to design the 3D printed models in such a way that expansion will be not outward but inward, so that it will not crack the shells. So that's another design consideration for the design for investment casting is different from the pattern for sand casting.
And also, since the 3D printed one is not solid, because wax is solid, there's going to be some expansion once it heats and melts. But for PLA, if it's going to heat up, and since there's a hard surface keeping it from expanding, and it's the melted plastic is softer. It tends to go the opposite way. So and then it merges off. So that's what happens.
Okay, so are there more questions from our face-to-face participants? Ayan, so meron pa po ba? So kung wala na, so meron pa pong questions dito from our virtual participants. So question from Sir David Erickson del Rosario. How can we make 3D printing attractive to PH foundries, Philippine foundries? The additional cost of the software and hardware and additional processes seems like a red flag for cost competition.
Ayun, I think that's a very good opportunity for me to promote our center. Yeah, because here at MIRDC, really, our mandate is to support the industry. And like us, me and Sir Lem really came from the metal casting industry, and we really have a special love for the industry. In AMSEN, we've started supporting different industries, especially from yun nga, sa metal casting. And if you are really skeptical about like investing in this kind of equipment, because you might not know how it will work for you or for your own like set of conditions on your foundries, you could go to us and try it out with us. I mean, we have the printers in the facility. We also really promote that we do R&D together with whatever like maybe you want to improve a process on your company, or you
Ito na
want
nga
to
eh.
develop a specific product that you're having trouble with. So why not let's work together on those kinds of challenges. In that way, you can be able to use yung mga printers, try it out for yourself and yourselves, and we can also train you on how to use it, how to design for pattern making, on how to do the design, on how to treat the designs, and the know-how para sa inyo, parang ma-absorb nyo, and then after that, you can decide for your own, knowing what you've experienced with what you've done hands-on. Masubukan nyo, matry nyo, and you can decide for yourself once the time comes na andyan ulit yung possibility that you really can use it for your benefit dun sa companies nyo. So yun po yung yun po yung isa sa mga So we'd be really glad if you can give us a visit, and we can give you a tour of our facility and also our other facilities, and we can show you how we can all work together to improve the industry, especially now na maraming challenges. Ayun po.
Thank you, Sir Joki. So we are inviting everyone to visit, no? MIRDC, especially AMSEN. Sir, how can they contact you? Para po kung willing sila to visit you po for this,
Ayan. We have a website. I think Amsen at DOST. Amsen at dost.gov.ph. You can also email us there. And what we usually do, I think, is you write a letter to our executive director requesting for like a plant tour or a facility visit, and then they will course it. I mean, they will assign us to do the tour. So yun po. Just visit our website and maybe send us an email for your intent to visit us.
okay. Thank you, Sir Joki. Yon. So you can email us at dun po sa email address na naka-indicate po sa aming website. You can visit www.mirdc.dost.gov.ph. Okay, sir, another question from Sir Paul Arman Sagib. Tama po ba na ang first step is 3D scanning? Then kapag may 3D model na, proceed to 3D printing then casting? Thank you po.
Ayun. That's correct, sir. But yep, you have two ways nga. If you can draw it with CAD software, if you can measure it and be able to draw it, mas maganda rin actually that you can be able to draw it, because being able to draw it from scratch with measurements, you have more control of your 3D model. Like if you want to change some thickness, if you want to change a feature like a hole or a thickness of a wall, you can do it parametrically because you've defined your drawing to have measurements. But if it's really impossible, like one of the parts I've shown you earlier, na it's basically impossible to measure and to be able to make an accurate drawing. You can always go with 3D scanning. The only drawback is since you made it with 3D scanning, you have no parameters to go back to if you want to change the features because it's going to look like let's compare it to like a document. If you have a Word file, you can edit the Word file if you have the Word file. But if you have a scanned file of a printed out document, you can no longer change the content of that scanned file, right? Because it's a picture file. So you can think of it like that. If you scan it, it's like a scanned picture file also that you can no longer change the information. So yun.
Okay. So another question from Sir Stefano Fernandez. How long does 3D printed patterns last?
Yun, Sir Steph, kumusta? uh, depends on how you make it. If you want to make it last for like 1,000 of parts, you design it to last 1,000 of parts. You define the wall thickness, you define the density. Also, you can do something with coating it with much stronger epoxy resins, or even maybe epoxy na masilya, ayun tawag, putty. So you can make it as strong as you want it to be. Of course, always considering how long you want it, how long you want to use it, depending on the volume and depending on the size of the part that you want to make.
Okay,
Yeah.
sir. Okay, sir, let's proceed with the next question from Sir Elgi Senita of the
Yes.
OST 7. Okay, so after sand casting, what are the ways in post-processing? Ordinary grinding lang ba?
For sand casting po.
Yeah. After sand casting, what are the ways in post-processing?
After
Or
sand casting, after you've casted the part, you go to the usual process of removing the gates and then doing shot blasting, and then you have the final casting. Or if it means the printing of the sand mold patterns, you do post processing, which is support removal. You do some sanding for those surfaces where the supports were removed, and then you do the coating afterwards. We have an online question po.
Ano pong type of printer or the brand affects the quality of the product?
Ayun po. So, type of printer or the brand. So, that's two different questions. The type of printer, I assume it means
1/3
type of
sa
technology.
orchard.
And
Doon sa
it's
pangalan
going to
niya.
significantly affect the
Sumeldo
quality
lang.
of the part. There are printers like the FFF printer, which is one of the cheapest ways to do 3D printing. It's going to make strong parts. At the same time, it's going to make very accurate parts. But up to s- just to up to some extent, it stops being very accurate when it comes to smaller parts. There are also printers that are able to make very, very precise parts, but with a different technology, like SLA. You start with a liquid resin, and light solidifies the part, and you end up with very, very precise parts. The limitation of those kinds of printer is the mechanical strength. It's not going to last long. So you have to choose which you want to make. When it comes to the brands, I think yes, there's a difference uh, in choosing like an expensive brand over a cheaper brand per se, but you can make up for that if you have like a cheaper brand. You can make up for that by playing around with the parameters. But if you're just you bought it at the same time and use it, the more expensive brands are usually more ready to use. You don't need to play around anymore with like I think it's like Apple. It just works. You don't need to optimize anything because it's optimized. The material comes from them. The database comes from them. The program comes from them. So there's not really much deviations because you've already controlled the system because you're working around their environment. Unlike if you buy something cheaper and it's more open, so you have to really do some work finding the optimal parameter for you to be able to do to make better quality prints from those printers. But it's not possible that you can achieve even a better quality material than with the branded ones. Yeah, readily if like you just use it readily, you will have like more immediate success with the more expensive ones.
I'd like to add to that, ma'am. The analogy is like this. If you're asking for the performance, right? Say if you're driving, you want to go there fast. Either you buy a fast car or you become a better driver. So you can buy a cheap vehicle, but you are a fast driver. You will go there, or you can go with a fast vehicle and that's so good driver. You can also go there. So so that's the difference. Yeah, a lot of it actually. Okay, so I think we can go now to the second part of the